Welcome back, Precalculus friends. We are up to section 7.5, day 2, which is our last section of notes for chapter 7. We're going to be continuing to talk about solving trigonometric equations today, but these equations that we're going to be solving are a little bit more complicated, so they're going to require us to do some either math tricks or some substitutions to solve. In our first equation, you'll notice that we have both sine and cosine. And so I'd like to do a substitution to simplify this equation. We know we have the Pythagorean identity, sine squared plus cosine squared equals 1. So if we solve that for sine squared, then that would give us sine squared x is equal to 1 minus cosine squared x. So the first thing that I'm going to do is I am going to do a substitution into this equation so that my whole equation is in terms of cosine only. So I've still got that 2 out in the front, and then I'm going to plug in my 1 minus cosine squared x minus cos x equals 1. And then of course I'm going to distribute the 2, so that will be 2 minus 2 cosine squared x minus cosine x equals 1. And then I am going to set this equal to 0, and I'm going to combine like terms. So I'm just going to put my 0 over here, and then when I combine like terms, I end up with 2 cosine squared x. I always like my a term to be positive, so essentially I'm moving all the terms on the left side over to the right side with the 1. So 2 cosine squared x plus cosine x minus 1, and that's equal to 0. So hopefully you recognize right now when you see this that this is going to be a factoring problem. We have a trinomial. Think of this as 2a squared plus a minus 1. So you could factor that any way that you want. I am just going to factor this by guess and check. And when I do so, I know that if I have 2 cosine squared x, that means that one of these has to begin with 2 cos x, and the other one has to begin with cos x. And if I have a negative 1 at the end, I know I need a plus 1 and a minus 1. If I want a positive 1 in the middle, then I'm going to put my plus 1 here to match up with the 2 cos x and my minus 1 there. And if I check my work, my inners make negative cos x, my outers make positive 2 cos x, which adds to make 1 cos x in the middle. Okay, so my factoring is done. I'm set equal to 0, so then I know the next step would be to use the zero product property to solve. So I've got my 2 possible solutions that are going to come from these 2 equations. The first one is going to be 2 cos x minus 1 equals 0, and the second one is going to be cos x plus 1 equals 0. So when I solve the left-hand one, I'm going to be adding 1, and then I'm going to be dividing by 2. So I'm going to end up with cosine x equals 1/2. Where does the cosine equal 1/2 when we think about our ordered pairs? Well, if we just think about those terminal points in the first quadrant, cosine is 1/2 at pi over 3, right? Here's our unit circle. So right here at pi over 3, we have a cosine value of 1/2. Also down here in the fourth quadrant at 5 pi over 3, we have a cosine value of 1/2. And again, we're looking for positive 1/2. Okay, so we get 2 solutions from our first part of the equation. Now let's take a look at the second part. When we solve this one, we get cos x equals negative 1. So then the question is, well, where on the unit circle is our x value of our terminal point negative 1? And that is right here at pi. So we are going to get 3 answers to this equation. Those 3 answers are going to be x equals pi over 3, x equals 5 pi over 3, and x equals pi. Now, because it said that the problem said to find all solutions of each equation, that means that we have to account for the fact that we can keep going around the unit circle over and over and over again. So every time we go around the unit circle, we're going to get another solution at each of these locations. So in order to account for that, we just have to add that plus 2k pi, which again just means that we could go around the unit circle one more time, or two more times, or three more times, or four more times, all the way to infinity. So this is going to be our solution set for this trigonometric equation. In our next example, we have sine and cosine again, but this time we don't have a squared term, so using a Pythagorean substitution is not going to help us. However, we do have this sine 2x term, which we could possibly use a double angle formula. So we know from our previous section that sine 2x is equal to 2 sine x cos x. So if we substitute that in for sine 2x, then our equation becomes 2 sine x cos x minus cos x equals 0. Now we still have sine x's and cosine x's mixed together. However, notice that now our two terms in our equation have a GCF of cosine x. So if we factor that out, that is going to help us a lot. So we take out the cos x, then we are left with 2 sine x minus 1 equals 0. And now that we've factored, we have two equations that are either just in terms of cosine or just in terms of sine. So our first equation here that we can look at will be cos x equals 0. And our second equation will be 2 sine x minus 1 equals 0. So let's take a look at cos x equals 0. Again, this is asking us, where on the unit circle is our cosine value 0? And that's going to happen in two places. It's going to happen at the top of the circle, which is pi over 2, and that's going to happen at the bottom of the circle, which is 3 pi over 2, right? Because the ordered pair here is 0, 1, and the ordered pair here is 0, negative 1. So the cosine value of each of those ordered pairs is 0. In the other equation, when we solve, we're going to be adding 1 and dividing by 2. So this is going to become sine x equals positive 1/2. And then we ask ourselves, of all the terminal points on our unit circle, where are the locations where our sine value, which is the y value of the ordered pair, where is the y value of the ordered pair 1/2? Positive 1/2. And that's going to happen in two locations because sine is positive in quadrants 1 and 2. And that is going to happen at our pi over 6 locations. So at pi over 6, sine is 1/2, and at 5 pi over 6, sine is equal to 1/2. So it looks like we're going to have 4 solutions to this equation, at least initially, although we may be able to do some condensing. So our solutions are going to look like x equals pi over 2, and again we're finding all solutions, so plus 2k pi, x equals 3 pi over 2 plus 2k pi, x equals pi over 6 plus 2k pi, and x equals 5 pi over 6 plus 2k pi. But what I want you to notice here is that our first two solutions, pi over 2 and 3 pi over 2, these two are always pi apart from each other. So we can condense this solution down and just say that both of these could be represented by x equals pi over 2, but instead of adding 2k pi, we would just add k pi, because every pi units, we will have another solution for that cosine x equals 0. The other two, the pi over 6 and the 5 pi over 6, those aren't pi apart, so we can't condense those down. So we're going to end up with 3 solutions to this equation, and they are right here. Our last two equations are a little bit different because they contain, well, this one contains, I guess we would call it a triple angle, and we don't have a triple angle formula for sine 3x. We only have a double angle formula for sine 2x. And then our last one contains an x over 2 in it. So we'll talk about that one after we do this one. But for this one, we're just going to kind of do a substitution. We are going to solve this equation as though 3x was just x, okay? So I'm just going to go about my business, but I am going to pretend that 3x is just like x, okay? So when I do that, first thing I'm going to do is I'm going to add 1 to both sides of this equation. So I'm going to have 2 sine of 3x equals 1. And then I'm going to divide everything by 2. So I'm going to end up with sine of 3x equals 1/2, right? And so again, if I'm just pretending that 3x is just like x, I'm looking for the locations on the unit circle where our sine value is 1/2. We know, we just did this in our previous example. We know that sine is positive in quadrants 1 and 2. And we know that the sine value, or the y value, is 1/2 at the ordered pairs pi over 6 and 5 pi over 6. Okay, so we're going to have those two locations as solutions. But remember, it's not that x equals pi over 6 and x equals 5 pi over 6. It is that 3x equals those. And again, because we are finding all solutions, we have to concern ourselves with that adding 2 pi k. We can't condense these two solutions because they are not pi units apart. So this is how we are going to write this. Okay, we're going to have 3x, because it's not just x, it's 3x, equals pi over 6 plus 2k pi. And we're going to have 3x equals 5 pi over 6 plus 2k pi. But now if we want to know what x equals, because we have a triple angle, we have to divide everything in our solutions by 3. So here's kind of the trick. We're going to divide by 3 to find out what x equals. So x is actually going to equal pi over 6 divided by 3 becomes pi over 18 plus 2k pi over 3. And then our second solution will be x equals 5 pi over 18 plus 2k pi over 3. Okay? All right. So these would be finding all of the solutions. Okay? Now, this particular example is asking us to find the solutions on the interval 0 to 2 pi. Okay? So now we have to go back and we have to say, well, we have our solutions for x, so what is that going to look like on the interval 0 to 2 pi? So I'm just going to write down here. My first solution, if k were 0, if k is 0, then my first solution, if I plug in 0 for k, is going to give me pi over 18 plus, and again, I'm looking right here, right? If I plug in 0 for k, then that becomes 0. So just pi over 18, right? My second solution would be if k equals 1. So then this would become pi over 18 plus 2 times 1 times pi over 3 would just be 2 pi over 3. So if I simplify that by making a common denominator, if I change 2 pi over 3 into 12 pi over 18, then this becomes 13 pi over 18. That's my second solution. And then finally, if k is 3, then I end up with pi over 18 plus, and if I plug in 3 for k, the 3 on top and the 3 on the bottom cancel, so I just get 2 pi. But if I rewrite this as over 18, right, and I simplify, my apologies, friends, I put k equals 3 instead of k equals 2. I don't know what I was thinking. I am going to finish this part of the example in my next video.